All right, good afternoon, good evening, ladies and gentlemen. Welcome to another series of tutorials with me, Aubrey. If you haven't already, please subscribe to the channel, leave a like, comment, and share, most importantly, so that more people get the same benefit you are getting from the lessons. Right, so this is part 6 of Mulungushi University. We're still looking at mathematics tutorial sheet 1. So if you haven't already, please go and watch part 1, 2, and 3, where I've explained most of the questions here. All right, so now this tutorial will focus on question number 3. This is where you'll be discussing the continuity of the following functions. All right, so continuity. Let me start by defining continuity in the simplest term I can. So we'll say if f of x is continuous on the interval a comma b, then f of x is defined f of x is defined throughout a comma b. All right, so this is the simplest definition of continuity. So if f of x is continuous on an interval a comma b, then f of x is defined throughout the interval a comma b. All right, so now discussing the continuity of functions, therefore, just means that we just need to find points where the function is undefined. All right, so what we know is that a function is undefined if its denominator is equal to 0. All right, so but the definition goes a bit above that. So but to determine if a function is continuous or not, we just need to equate the denominator to 0. And if there is nothing we can do about that function to simplify it such that it is defined, then we conclude that the function is undefined. All right, so for this one, we equate this to 0, x is equals to 0, the denominator to 0, and we see that when we have 1 over 0, it will be undefined at x is equals to 0, and there is nothing we can do to simplify this function for it to be defined. So we conclude that f of x is undefined at x is equals to 0, and we are done like that. So that is the continuity of this function. F of x is undefined at x equals to 0, therefore not continuous. Okay, therefore not continuous. All right, so we go to b here. So if we do the same for b, we see that when we equate this to 0, that will be x is equal to, sorry, that is x minus 1. We equate that to 0, we get x is equals to 1. So this function is undefined at x is equals to 1, because when we replace there 1, we have 1 over 1, 1 minus 1, 1 minus 1. That is a 0 over 0 case, which is undefined. Is there something that we can do to this function such that it is defined? All right, so we see that on top here, what we have, that is a difference of 2 squares. So that can be written as x plus 1 times x minus 1. We see that at the bottom we also have x minus 1. So which this and that simplify, and we have f of x will be equals to x plus 1. And we see that this is a linear function. All linear functions are defined. Okay, all linear functions are defined. So we see that f of x is a linear function and it is defined. So what we say in this case is that we say f of x is defined okay, we'll say this. Let me do this. All right, so we have f of x and brush. All right, so we're going to have f of x equals to x plus 1 as our final function. So now the conclusion will be f of x is continuous. It is continuous, but has a removable discontinuity at x is equals to 1. So that is how you'd discuss the continuity of this function. So we see that this function, when simplified, it is continuous, but when we plug in directly, it has a removable discontinuity at x is equals to 1. All right, so that is that. And what you should know is that all functions that do not have a denominator are more likely to have to be continuous. So like a polynomial is continuous everywhere. We see that this one is continuous. All functions that do not have denominators are more likely to be continuous. So like here, this is a quotient, so this is less likely to be continuous. So that is just a food for thought. All functions that do not have a denominator are more likely to be continuous. So all functions that do not have a denominator are continuous in terms of the variable. If the variable is not in the denominator, then it is likely to be continuous. All right, now we go to h. H, here we have to be very careful. This is a piecewise function. By piecewise, we just mean that the function is made up of two parts, and those two parts are guided by an interval like this one that is here. So when you're looking at a piecewise function, what you should look at is the interval here that you have here, the interval that is guiding these two piecewise functions. How you read this function is just the same. You just say this is the same thing as y is equals to x plus 1 if x is less than or equal to 0. Then this one can be read as y is equals to x squared plus 1 if x is greater than 0. So these are two functions, then they are guided or they are joined by these two inequalities that are here. So we just have to look at these two inequalities. So if these functions are joined by these two inequalities, we say they are continuous. But if they are not joined by these two inequalities, we say there is a discontinuity. All right, so we plot our simple XY plane there, right? So that is our XY plane. Now we analyze this one. So if x is less than or equal to 0, so x is equal to 0 is on this part of the graph. Let me just draw it. So x is equals to 0 is on this part of the graph, that is x is equals to 0. And we see that x is less than or equal to 0, meaning that 0 is also included in this interval. All right, so 0 going this way. Okay, so we have this function. All right, now we look at this one, x greater than 0. So greater than 0 meaning that 0 is not included, meaning that we are starting from above, a bit above 0. So that is somewhere above 0 there. All right, okay, so above 0 going this way. And this is of course a quadratic here, which has a positive that has a minimum there. So it will be something going through one like that. So we see that these two functions are discontinuous at x is equals to 0. There is that gap there. They're not meeting on that gap. All right. So we conclude to say h of x is discontinuous or is discontinuous on the interval. So this is the interval that we can write, or maybe we can just say at x is equals to 0, there is a discontinuity there. So h of x is discontinuous at x is equal to 0. So that is about that function. It is discontinuous at that point. All right, so we move on to D there. All right, so for D, this one is a straightforward question. Okay, so for D, we see that when we equate root of x, when we equate root of x to 0, we see that x is equals to 0. So we say f of x equals to 1 over root of x has a discontinuity at x equals to 0. So has a discontinuity at x is equals to 0, and that is about discussing the continuity of the function. So if you didn't understand anything, or if you have questions, please leave them in the comment box or reach out on my WhatsApp, and I'll be able to answer those questions. So but for now, this is about it. So in the next lesson, we'll be looking at evaluating integrals using evaluating derivatives using the first principle. So we'll just be differentiating these using the first principle. Then we'll go on to evaluate these other derivatives, and that will be much about the tutorial. So if you haven't already, please subscribe. Have a good evening.